Imagine you need to wire a dozen isolated facilities into a single power grid using the minimum amount of copper wire. Finding that efficient layout is the minimum spanning tree problem. Kruskal's algorithm solves this by evaluating the entire network at once. Instead of starting at one specific location and growing outward, Kruskal's approach is globally greedy. It scans every possible connection across the graph and selects the cheapest options first. Let's run the algorithm on a graph. We have 5 nodes, A through E, and edges with defined weights. Kruskal's first step strips away the spatial geometry, organizing the raw data into an edge list. Then we sort the edges by weight in ascending order. This process converts a spatial geometry problem into a linear sorting task. At the start, every vertex belongs to its own set. We begin at the top of our sorted list. The cheapest edge is A to B, with a weight of 2, so we add it. Because A and B were separate, we perform a union operation, merging them into a single component. Our running cost is 2. We move down the table to the next cheapest edge, B to C. It is independent, so the edge is accepted. The set expands to include node C, and the cost becomes 5. We repeat the process for C to D. D is independent. We merge the sets, and the running cost reaches 10. Next is the edge from A to C, carrying a weight of 6. The algorithm runs a find operation on both nodes. It discovers that A and C already share the same parent set. A tree cannot contain closed loops. Since adding this connection creates a cycle, the algorithm rejects the edge. The final valid edge is D to E, with a weight of 7. This links the final isolated node to the main structure. All vertices are now connected, forcing the algorithm to terminate. Our completed minimum spanning tree has a cost of 17. By selecting the cheapest valid edge at every step, the algorithm constructs a tree that connects all nodes at the lowest possible total cost. We have the structure, but how much computational power does this process require? The first step requires sorting all available edges. Efficient sorting algorithms complete this task in O of E log E time. The second step processes every edge using union find cycle detection. This requires O of E times alpha V time. Alpha V is the inverse Ackermann function. Its growth rate is so slow it functions as near constant time. Combining these costs gives our overall time complexity equation. Because cycle detection is nearly instant, sorting dominates the runtime. The final time complexity simplifies to O of E log E. Ultimately, Kruskal speed is strictly limited by exactly how fast a computer can sort a massive list of numbers. How can we prove that these greedy choices produce the most efficient possible layout? We can prove it using the cut property. Imagine a line dividing a network into 2 distinct groups. Multiple edges cross this divide. Kruskal's algorithm identifies the cheapest option, edge E. For the exchange argument, assume an alternative tree ignored edge E and chose a heavier edge to bridge that gap instead. We can test this by swapping the heavy edge out and putting Kruskal's chosen minimum edge back in. This swap guarantees 3 results. The graph remains fully connected, no cycles are created, and the total weight decreases. Because this swap is always possible, an optimal tree must contain Kruskal's chosen edge. The exchange argument proves that Kruskal's greedy strategy always results in a mathematically optimal minimum spanning tree. Kruskal's strategy is effective, but it functions differently than the other major approach, Prim's algorithm. Prim starts at a single vertex and grows one tree outward. Kruskal starts with disjointed sets, merging them edge by edge. Prim is best for dense graphs with many connections. Kruskal is better for sparse graphs, sorting a smaller list of distinct edges. Structurally, Kruskal requires O of V plus E memory space to store the edge lists and disjoint sets. To remember Kruskal's sequence, use the acronym SSFUR. Sort the list, select the smallest edge, find sets, union sets, and repeat. That concludes our analysis of the minimum spanning tree. You have the tools to link environments using the fewest possible resources.
But if you need to get from a specific starting location to a destination as fast as possible, you need a different tool. That is the single source shortest path problem, solved by Dijkstra's algorithm. Mastering algorithms means recognizing that the shape of the data dictates which mathematical tool is required to process it.